paper we will discuss today is the IFMIF-DONES project Preliminary Engineering Design. Chapter 1.3 Accelerator Systems. The IFMIF-DONES accelerator is a sequence of acceleration and beam transport stages. A schematic accelerator configuration is depicted in Figure 2. A CW140 mA deuterium beam is produced and extracted from an electron cyclotron resonance ion source at energy of 100 kV. A low energy beam transport section guides the deuterium beam from the source to a radio frequency quadrupole RFQ system. The RFQ branches the beam and accelerates the full 125 mA current to 5 MeV. The RFQ output beam is injected through a medium energy beam transport MEBT with two rebranching cavities and then transferred to a superconducting radio frequency RF. Linac, where it is accelerated to a final energy of 40 MeV. Finally, a high energy beam transport HEBT line guides the beam up to the target and at the same time, shape is beam to a rectangular shape with the help of non-linear magnet elements. The HEBT also includes a beam dump developed to stopping the beam during some specific commissioning and startup phases. Based on the result of the released beam dynamics analysis, the superconducting RF Linac will consist of first separate cryomodules which house superconducting cavities and solenoids which characteristics as given in Table 1. All the accelerating RF cavities are powered by a radio frequency system based upon use of 175 MHz. High power solid state amplifies with a CW output power level up to 200 kW, a total of around 54. Such amplifiers are needed, one for each accelerating cavity and an additional 8 for powering the FRQ. Additionally, the MEBT is powered by two smaller solid-state amplifiers rated at 20 kW CW. The main parameters of the IFMIF-DONES accelerator system are described in the Table 2. Chapter 1.4 Lithium Systems. The lithium systems are broken down into several subsystems according to their functions as per Figure 3. The target system consists of the components situated in the test cell and the beam duct up to the target interface from room TIR. The system shapes the lithium target and positions it inside the test cell with respect to the beam and the high flux test module. The main component is the target assembly TA, which includes a concave shape open channel back plate exposed to the accelerator vacuum, presenting a stable lithium jet to the beam in which the kinetic energy of the deuterium beam is deposited and where neutrons are produced. The heat removal system comprises the main lithium loop and its dump tank, recirculating the lithium between the TA and a heat exchanger, and a secondary and a tertiary oil loop transferring the heat to the plant general cooling water system. The system is designed to evacuates the heat deposited in the target and to control and maintain a consistent lithium temperature at the TA inlet. Irrespective of the beam power, all oil loop contain a branch line to bypass the heat exchangers and control the lithium temperature. The impurity control system consists of a branch line which extracts a fraction of the lithium from the main loop and rejects it after purification and impurity analysis. The system is designed to condition of lithium after maintenance prior to startup, and control and maintain a defined level of purity. The purification branch contains a cool trap to remove elements with temperature-sensitive solubility in lithium, mainly CO and metallic impurities, most related to corrosion and activation products as binary or ternary compounds, and the hydrogen trap to remove hydrogen isotopes by chemical reaction with hydrogen binding material presently. It is also planned to maintain nitrogen content at a low enough concentration in the range of 30 ppm by installing a nitrogen binding material presently to lithium inside the lithium loop dump tank to be used during the maintenance operations. Lastly, the gas and vacuum heating electric power supply and lithium and oil recovery system make up the so-called lithium systems ancillaries. Figure 4 shows an expanded view of the complete lithium systems. Thanks for listening to the end of today's show.